Now let us talk about the reversible isothermal process. Now when an ideal gas of mass m undergoes a reversible isothermal process from state 1 to state 2, the work done is represented as integral from 1 to 2, and then you write down dW. Now this is equal to P into dV, that's the change in volume, and the volume changes from V1 to V2. Okay, now what is not changing in this is temperature. So I would say T1 is equal to T2. Okay, so when I solve this integral, I get W1 to 2 is equal to, so now if you look at the value for P, because it's an ideal gas, so the value of P would be mass into R into T. So I'll substitute the value of P, that is mRT upon V in place of P over here. So it would become V1 to V2 into mRT into dV upon V. Now M, R and T, all these three things are constant in this kind of a process. So we'll take them outside the integral sign and we would have log of V2 by V1. Now we know that the volume is inversely proportional to the pressure. So I can write down that work from 1 to 2 is also equal to mR into T into log of P1 by P2. Now, after getting a relationship for the work done in going from state 1 to state 2, let us now find out the heat transfer that is involved in the process. So heat transfer in going from 1 to 2 is written as Q12. This is equal to the change in the internal energy in going from 1 to 2, that is U2 minus U1, plus the amount of work that is done in going from 1 to 2. Alright, so from this equation, I know that the value of U2 minus U1, this is equal to 0, because we know that internal energy is a function of temperature, and because temperature is constant, the internal energy change would be 0. Alright, so I can say that Q12, this is equal to W12. Okay, now what is Q equal to? Q is equal to T into the change in entropy. So I can write down that Q12 is equal to the temperature into the change in entropy in going from state 1 to state 2. So that is S2 minus S1 is equal to M into R into T into log of V2 by V1. So this is a relationship that we can straight away use for a reversible isothermal process for an ideal gas of mass M. Okay, so I hope you understood this very small analysis. Now let's move on to the next topic and talk about the polytropic process.